Hello, we are presenting the Florian project, a system for relative position tracking for firefighters. Our faculty advisor is Dr. Dawn Estrich, and our industry advisor is Michael Vargas, and our client is the Roseville Fire Department. Project information can be found on our website, theflorianproject.com.
I'm Austin.
I'm Brandon.
And I'm Corbin.
This is an overview of our presentation. First, we will discuss the problem and the existing solutions. Next, we will describe our proposal and show a brief demonstration of the system. We will then cover the marketing and engineering requirements. We will also go over our design choices and our system overview, and then the challenges we have faced and resulting changes. After that, we will go over the tests we have conducted, then we will show our final product, briefly discuss the bill of materials, our schedule, courses which have supported our work, and then cover any questions you have.
The problem that we are looking at is that according to the U.S. Fire Administration, there have been 76 firefighter deaths in the last 10 years due to either being caught, stuck, lost, or disoriented. This is because there's no method of knowing who or where each firefighter is in a burning building. There's also no way to quickly notify where a team member is if they are trapped or injured. These are two of the most used solutions. The first is the pass device, which emits a loud alert when firefighter stops moving for 30 seconds. It is very easy to use for as long as it is on. It is detecting whether there has been motion or not, and is reliable in fires. But after talking to firefighters in the field, we found that it only works if others are nearby, and even then it sometimes is ignored due to lack of training or oversensitivity leading to false alarms. It is also expensive, as a single unit costs anywhere between $500 to $700. The second option that is used in the field is a polyurethane rope. The rope is cheap and intuitive, but it is also heavy and can get in the way because it can be hard to see during a fire.
This picture is an example of what we imagine this system could look like, with the positions of firefighters shown, along with the paths that they took to get to their current locations. For the scope of this project, we were unable to test fire resistance or operation in smoke. While we recognize that this is something important, it's just something that we did not have the capacity to do.
And here we have a demonstration of the system. The large video shows an individual walking around our trackable area with a tracking tag. The small video shows the tracking screen with the path that the individual has taken in red. This screen shows the user interface with a tracking tag which has stopped moving. After 30 seconds of inactivity, a message appears notifying the user that the individual has stopped moving. The marketing requirements for our project were developed after talking with our client and with other firefighters. For our system to be effective and adoptable, it would have to be able to work on most single-story homes in the US and accurately provide the locations of each firefighter. The system would also need to feature rechargeable batteries and operate for a minimum of 3 hours. Current safety systems monitor for firefighter inactivity, and our system would need to as well. At the scene of a fire, there may not be a reliable internet connection, so the system would need to provide the location data without an internet connection. To keep system costs low, it would need to make the location data available on smart devices that the firefighters already have. The system will also need to be set up when firefighters arrive at the fire, so deployment time will need to be kept to a minimum so that it does not interfere with firefighting operations. Finally, the tracking modules, the tags, that are worn by firefighters must be small and light enough to not affect their mobility. These are the engineering requirements for our project. The items that are marked in red are aspects that have been changed and will be discussed shortly. The first requirement is that the system will be able to track firefighters through walls made of wood, drywall, and stucco. The second requirement is that the system will track firefighters within a 30 meter by 30 meter square with an accuracy of 1 meter. The third requirement is that the tags will have a battery capacity of at least 600 milliamp hours. The fourth requirement is that movement data will be used to detect if an individual has not moved for 30 seconds. The fifth requirement is that a single board computer will host a SQL database, a web server to visualize the data, and provide a local area network over a Wi-Fi hotspot. The sixth requirement is that the deployment time will be less than 5 minutes with one person. The seventh requirement is that the tags will be smaller than 8 centimeter by 10 centimeter by 4 centimeter and weigh no more than 1 kilogram.
We first started by looking at a few methods of tracking wirelessly. GPS has an unlimited range, but is also only accurate in outdoor situations. While Bluetooth could be accurate enough for indoor use, its maximum range for tracking wasn't far enough for our project, and Wi-Fi would not be accurate enough. That's why we chose ultra-wideband, because it works both indoor and outdoor, and both its range and accuracy are sufficient for our project.
TwoWay ranging is how we can use ultra-wideband to determine distance. To start, we have a stationary tag at 0 meters, a stationary anchor at 0 meters. A tag, which is our moving target, then sends a signal to our anchor. The anchor then receives this signal and sends the signal back. The tag can then use the time it took for the signal to be sent there and back, multiplied by the speed of light, and then divided by 2. This gives you the distance from tag to anchor. This distance is then reported back to the gateway, so we have access to that data. If we now have a minimum of 3 fixed anchors with known positions, we can compute a location of the tag relative to the anchors using some simple geometry. Once the location has been computed, the tag will be reported back to the gateway, which will be located on the fire truck. The geometric approach to finding the position from distance is called trilateration and can be done in both 2D like this or in 3D with a z-coordinate. This is the 3 stages of our system overview. The first on the left is the tag/anchor. This simply consists of a battery with an ultra-wideband module. This then communicates via ultra-wideband to another module configured to be a gateway that communicates with the Raspberry Pi via a serial interface. The Pi then creates a wireless access point for devices to connect to that is hosting a web server that shows the positional data being plotted.
After some research, we found that most projects using ultra-wideband tracking use modules from Decawave. So we chose to use the Decawave module DWM1001C. We chose this module because its specs were optimal for our uses and can be programmed to be used as an anchor, tag, or gateway. We quickly found out that while the accuracy of 10 centimeters is to specs, a range of 75 meters is ideal, and we had trouble getting connection at that distance.
The printed circuit board, PCB, that we designed incorporates the ultra-wideband module as well as the pins for programming the module, a Raspberry Pi pin header for use as a gateway, and a charging circuit. The charging circuit is shown below, and the PCB is shown to the right. The charging circuit will monitor the charge rate and the voltage of the battery and discontinue charging when it's complete. It is charged using a standard 5-volt USB charger and micro USB cable. The battery contains a protection circuit which will turn it off after dropping below a certain voltage, so our circuit will not need to handle that.
These are 2 protocols we are using within our project. To actually receive our positional data, that is accomplished through the MQTT protocol. This is because there are strict timing protocols for communicating between our gateway tag and the Raspberry Pi. So to keep those strict timings, they only allow the data to be accessed through an MQTT server. The next is Redis, which is being used as a caching system between Python scripts, so data can be passed to different blocks of the system. Here is a closer look at our software. On startup, we make our connection to our ultra-wideband modules. The web server and wireless access point is then started, and the positional data is then read from the gateway module. The data is then passed via Redis to the web server, where we will wait for the next MQTT message. On the web server side, we read in the data point, shift the older points down through an array to be plotted as the previous location. We plot the new location and then wait for our next update interval. The system also has a 30-second interval that is asynchronous from the graphing. It waits till 30 seconds has passed. If there's been movement during that time, no alert will be sent, but if there has been no movement, the alert will pop up. The data acquisition part in the red box was one of the most difficult parts of the project. When you read MQTT data with Python, it is done with a locking process. The web server is also a locking process, so they could not be running within the same Python program because one would always be locking out the other and they wouldn't both be running. This led to the discovery of Redis, which allows me to pass the XY data into the actual web server to be plotted. Here is what our tracking interface currently looks like. The main gray square is where the locations are being displayed. While the graph may look small, the screen is zoomed out to allow you to see the text at the top of the screen. Normally the graph nearly fills the screen. And then here's what we would have liked it to look like, with the operator being able to sketch in notes on top of the graph, marking things like entrances and exits, windows, and other important landmarks. And then this is what the system looks like when it doesn't detect movement. A pop-up alert is put on the screen, and the operator must confirm before they can continue to use the system.
When we began the project, we thought that we may have problems with the device orientation due to the radiation pattern of the ultra-wideband module's antennas, or problems with anchors going offline. So far, these have not been problems. We have had problems with SQL, Ethernet, and Wi-Fi, problems losing our wireless connections at the edges of our testing area. Solution to these problems was to replace SQL with Redis, disable the Ethernet port on the Raspberry Pi, and to change our anchor distances. We have also seen challenges from the COVID-19 pandemic, which will be discussed next. Changes we have made after testing include Engineering Requirement 2 and 5. Engineering Requirement 2 has changed from tracking a 30 meter by 30 meter square to a 20 meter by 20 meter square with outdoor testing only. While the total trackable area has changed, the total size of a house that a person can be tracked within has not changed. We will still be able to track in over 90% of US homes based on square footage. We have also restricted the testing to outdoors only in order to comply with current shelter-in-place orders. The second change that we have made is to eliminate the SQL database in favor of a simpler method using Redis. This change is because the SQL database is unnecessary for our needs, and Redis is able to be used instead and simpler. And we have performed all but one of our planned tests. All of the tests that have been performed have passed. The one test we have not performed is our signal passing through walls using the full system, and we will not be able to perform it due to the shelter-in-place orders. A notable system test is System Test 2.2.2, the operable range and location accuracy. This test originally failed, but it has since passed, and it will be discussed shortly.
This test that was conducted was a test to see if the signal from the modules would pass through walls. We started on either side of a wall, 2 meters apart on either side, and checked for communication. We then moved backwards in intervals of 2 meters to a total of 8 meters from the outside wall. At this distance, the system was communicating both through an interior and exterior wall at a total distance of 10 meters. From this test, we were able to confirm that the system can accurately communicate through walls.
This is our single module operable range and accuracy test, where we confirm that the ultra-wideband modules are able to report distances accurate to 1 meter and at a sufficient range. The image shows one module at the 0 meter mark and another module that is started at a 6 meter mark. The module at 6 meters was then moved further apart until the connection was lost. We expected to see that the modules could operate at least 30 meters from each other and report the distance within 1 meter. The result of this test is that the modules were able to accurately report distances up to 45 meters away. Our conclusion from this test is that the ultra-wideband modules will be able to accurately provide location data at the distances required for our project.
This is our first full system test. We started by measuring out a 30 by 30 meter square. When we first placed the anchors and attempted our test, we were having unreliable connections with our modules and anchors, disconnecting constantly. We then decided to move the anchors into a smaller area to attempt and reconduct the test. After confirming the connections, we continued on by choosing 6 random points, along with 2 corner points. We then started at 1 point, waited 5 seconds, and recorded what the tracking interface said the current location was. We then moved on to the next location and repeated. We did this for a total of 10 times at each location, changing locations in between each new reading. In order for this test to be successful, the average of all test points at each location needed to be within a 1 meter radius of the actual location.
At this distance, we were able to achieve our 1 meter radius accuracy at all but one location, which is the 5,16 point. However, this data point is just barely outside of our threshold. We believed that there was some human error associated with the measuring of the X and Y coordinates of the testing locations. Because of this, we decided to completely redo the test, starting from scratch and remeasuring everything much more carefully. This resulted in a much better test, as you can see based on the graph on the right.
Our system has battery-powered tags and anchors, and it must operate for a minimum of 3 hours. The battery capacity is based on the required runtime of the system and the maximum current draw of the module. By multiplying the required runtime and the maximum current draw, we get the minimum required battery capacity in milliamp hours. Our battery life test measured the battery voltage of a module during continuous use. The module was configured as a tracking tag with a 10 Hz refresh rate and had a probe connected to an Arduino analog to digital converter to measure the voltage of the battery. The voltage read by the Arduino was monitored by a LabVIEW virtual instrument and recorded the voltage over the elapsed time of the test. The module battery voltage remained above the module's minimum operating voltage of 2.8 volts for about 6 hours. The test ended when the module was no longer online despite being powered. The module still operated normally for about 6 hours and will be able to allow the system to operate for the minimum of 3 hours.
Our next test was testing the ability of the system to be able to accurately check for inactivity. To do this, the system was set up as normal, and Corbin walked around for 1 minute. This was to confirm that an alert would not be sent with movement. Then I had him stop moving and timed how long till an alert came through. The average time to alert was about 34 seconds. However, the system only checks every 30 seconds, and we allowed for a plus-minus 5-second buffer, so this was a pass. We next needed to test if Redis was reliable and could accurately cache data. To do this, I set up a Python script that generated 20 random numbers. These were then cached inside Redis. In a separate script, I then read from Redis and compared the sent value to the values I got. This resulted in 100% accuracy, and it was determined that Redis was accurate enough for our needs.
We finally tested how long it takes to deploy our system. For this test to be successful, our deploy time needed to be less than 5 minutes with one person. To set this test up, we needed everything off and unplugged. We started a timer and timed how long it takes for one person to set the tripods up around our test area and connect to our app to start tracking. We did this test 5 times. Each test took less than 5 minutes with an average of 3 minutes and 47 seconds. Because of these tests, our setup time is fast enough to not hinder firefighter operations. The cases for our tags need to be small enough to not obstruct movement for firefighters. For this, we modeled cases in SOLIDWORKS and 3D printed them. The outcome is a case that is roughly the size of a deck of cards at 7 centimeters by 8 centimeters by 3 centimeters and weighs 83.5 grams, which passes our requirements. The case made has a power switch on the side, large enough for heavy firefighter gloves to handle, a magnetic lid for easy access to the module, and a 1/4-inch screw hole. This is what our final product looks like: anchor, GUI, and tag. The 1/4-inch screw hole fits most tripods in order to be used as an anchor, and also can be used with an eye-hole bolt and a carabiner, which was recommended to us by the firefighters to be worn as a tag.
My contribution to the project was the complete back end of the system. Everything from getting in our coordinate from the tags via MQTT to graphing, keeping track of previous locations, and alerting the user to inactivity.
For the project, I worked on designing the printed circuit boards for the tags and the anchors, designing a charging circuit, and flashing the module firmware.
I handled the networking side of the project, turning a Raspberry Pi into a local hotspot, and I also designed and built the final case to be easy to use and intuitive. This is our bill of materials. We are under budget at $607, the largest amount going to a Decawave modules. This is our full Gantt chart. On the next slide is our condensed Gantt chart, which the first star that you see on the bottom right is the first full system test that we did. The smiley next to it is the point where we're on track with all of our tests, but then next to it is the cancel sign where we were supposed to have our last and final test, but that was the week that we also went into quarantine. The last star on the right is the star where we actually did our last test 4 weeks behind schedule. These are some of the future works that we would like to do given more time. We like to complete indoor testing as we are not able to complete that portion of the project. We would like to make the system functional with multi-story homes and around smoke and fire. Some additions we would like to make like to add to the project are a heart rate sensor to view vitals and GPS so our system can be used in larger scale fires such as a wildfire. We also would like to add an autonomous anchor position calculator so the anchors could be placed at different points around the house rather than a perfect 20 by 20 meter square. These are our references, a few supporting courses. We'd like to thank Dr. Don Estrich and Michael Vargas for putting in many hours to guide us through this project, to the Office of Research and Sponsored Programs for funding this project, to the Roseville Fire Department for being our customer and much needed feedback, to the SSU EE Department for the continuous support for the past few years, and to our friends and family who have had to live with us for the past year. Thank you. Any questions?
Thank you very much. And could you show us the page where you have your contacts, name and contact information, please?
Next slide.
Okay.
Oh, next slide.
Perfect.
Okay.
Next slide, yeah. I'll put it right below.
Okay, very good. So I would just like to remind everybody to complete the evaluation form. The link to the evaluation form is in the chat box. If you are not able to see or access it, the URL is https://tinyurl.com/SSU EE 2020. So if you're still having difficulty, please send me a message in the chat, and I'll try to get you the URL. But thank you very much for completing the evaluation form for this group. And now this is time for question and answer. Please use the raise hand feature so that Joshua.
Can you guys hear me?
Yeah.
Yes.
Yeah, I had a question. You talked about future plans and making this into a heart rate monitor, adding GPS, being able to detect two-story homes. What is the expected cost and the physical changes, the size and weight? You know, you guys were talking about constraints. What is that going to do with that handprint of the unit and the cost of the unit if you were to add that stuff in?
So the module has a microcontroller already on board with it. So adding the extra sensors onto it we wouldn't have to add much more hardware for that part. A heart rate monitor would have to go onto someone's skin, so that wouldn't be included in the size of the of our case itself. We would, however, need to add a way for it to transmit that data, so that would add some size into our case, but we do have some extra space in there. So I think it would still fit within our size and weight requirement. The weight requirement or the actual weight of the case with the module inside is not close to our maximum weight. As far as estimated cost goes, I'm entirely sure on that. Austin or Corbin, do you have an idea for that?
Not totally sure about cost. We could definitely get that too. Based on our budget, we did buy excess modules, so that could that factors into the cost as well. The system is expandable though, so for what we have right now, if we wanted to potentially add more firefighters to be tracked and potentially increase the area, we would simply just have to include more of the anchors and possibly a second gateway depending on how big we made it. But the system is already there and it's could be expanded pretty easily.
Okay, very good. Next question from Rob.
Yeah, thanks, guys. Wonderful presentation. I'd like to know how your interaction with the fire department went. What kind of comments did they make? Because they're usually pretty critical people.
So we originally tried to get in contact with Roanoke Park Fire Department and the fire district around here, and that was last year, and I believe that was around the time there were some fires going on, so it was a little bit difficult. So my dad actually works for Roseville Fire Department, and so that's how we were able to get in contact with them and have a conversation with them, and they seemed very interested in the project. and they liked where we went with the project, and they would obviously love to maybe eventually see something like this being deployed around fire stations or at fire stations for them to use.
Do you see scope for being involved in one of their exercises at some point? I realize you're coming to the end of the semester, but isn't that something that would be kind of good to do?
We would have loved to do that. I think our biggest hurdle at this point was that we haven't been able to really do any testing with fire resistance. So if we were to, be able to deploy this with one of their operations, we would just be worried about that, since that's not something we were able to really test for and plan for at this point.
Thank you.
Okay, thank you. So next question is Joe.
Yeah, you guys mentioned that you were interested in automating the setup of the anchors. Do you have a rough idea of how that would occur?
We were originally planning on figuring out exactly how we would implement this. That was going to be done just a few weeks ago. And as soon as we were going to start working on that is when school transitioned to online only, and that kind of put a bit of a speed bump in our way. So we lost a bit of time in that, and we weren't able to actually complete our plan for implementation for that because we were trying to figure out how to finish the rest of the project with what we could do during that time.
Okay. So next question from Joaquin.
Yeah, one thing I noticed that you were saying that with one person the system could be set up in 3 to 4 minutes, but that seems like it would be quite a long time in the context of fighting a fire. So you mentioned you were thinking of automating it, but what other ways were you thinking of shortening it? Were you thinking that multiple firefighters setting up the anchors would shorten the time needed to start it, or they'd be set up beforehand, or what?
Do one of you guys want to take that, or want me to take it?
I'll do it. So we were mostly focused on not setting up during an actual active fire right now. We were with our interviews with the fire departments and firefighters. We found that a very dangerous time for them to be in the building is not just during the fire, but also after the fire. They could be there for hours after the fire has been extinguished, cleaning up, and still inside the building. And even after the fire is extinguished, there are still a lot of hazards. The building could be unstable and other problems. So we weren't entirely focused on doing it during an active fire. I think we had a little bit extra time that we could. Our time budget for setup was a little longer than if we were trying to set it up during an active fire.
On the other side of that, definitely the time could be sped up while if multiple firefighters were placing these around the building. As far as like setup time goes, the longest time is actually physically going around the house to the locations to place them around that. So that if we could eliminate that with multiple firefighters, that could definitely cut down on the time to deploy.
Okay, thank you.
Okay, Chris.
Yeah, thanks for a great presentation, guys. A lot of hard work getting to this point, so I appreciate it. So my question is simple. What's the most important thing that each of you learned during the course of the project?
I think that the most important thing, and you harped on it from the very beginning, is time management. And I think the other thing is definitely working on the report and the presentation slides in the very beginning. We tried to be as good as we could, I feel like, but it definitely would have helped in the long run to be working on things from a lot sooner in the project.
I think probably the most important thing I've learned is, as you've said many times, do the research. And as much as we've felt like we had done sufficient research during the beginning and actually during every stage, there's just always more that could have been done. And so I think really not trying to get carried away with trying to get something started, and really just focusing on research early. Probably could have saved a little bit of time, and was also a valuable experience.
I thought that learning how to create a story or tell a story around slides. This is very beneficial because I spent a lot of time going through the flow of this and seeing how it felt, going through it multiple times, seeing, oh, that doesn't fit there. I'll maybe go up one slide or down two slides, something like that. That was very challenging too.